Today, I would like to talk about how a friend and I found a new and beautiful way of looking at magnetic fields and vector fields more generally. As a graduate student doing theoretical physics, my job is to find mathematical models that help us understand physical phenomena. This work is as much about finding the right questions as it is about finding answers, and indeed the result I'll be sharing came from asking a question about the physics of plasmas, but then following the adventure it led us on. We discovered a way to encode important information about the structure of a magnetic field in something that looks surprisingly like an electric field, and even has objects that look like moving point charges. In the process of sharing what we learned, I hope to also shed some light on the creative process behind theoretical physics. Since this video is mostly the story of the discovery of a new mathematical tool, it's going to be a bit more math-heavy than my previous video, with vectors and calculus making an appearance. I've tried to condense most of it into a single section, with the rest driven as much as possible by visual arguments. I hope you'll join me for the ride. This story starts a few years ago, when my friend Chris knocked on my office door with an idea. Picture the magnetic field of the Earth. It's mostly quite similar to a bar magnet, pointing out at one pole and going around to the other pole. This field does not exist in isolation, though. It is embedded in a field emanating from the sun. Chris wanted to know if there was a simple way of solving for the places where these two fields cancel out, pointing in opposite directions and producing a point where the magnetic field is zero. These points are called magnetic nulls. The reason this question interested Chris is that these locations where the magnetic field goes to zero carry special importance. The sun is constantly emitting a stream of plasma in all directions. This plasma is constrained to follow magnetic field lines. As it flows past the Earth, it interacts with the Earth's magnetic field, producing the aurora. At points where the magnetic field vanishes, there is no field for the plasma to follow, producing complex behavior that is an ongoing area of study. Chris was also curious about the problem of finding magnetic nulls in general, since similar points appear in many other places, such as the magnetic fields of nuclear fusion reactors or in loops of plasma in the solar corona. The framing of the problem went something like this. Consider some magnetic field which is localized, meaning it is produced by some object of finite size and tends toward zero far away from the object. For concreteness, we'll picture the example of the Earth's field. Call this the local field. Now add on a uniform field pointing in some fixed direction with constant strength, say the field of the sun. Call this the external field. Generally, there will be some points where the local field and the external field precisely cancel. Nulls. Chris's question was twofold. In general, how do you calculate where magnetic nulls will appear? And if you change the external field, perhaps as the Earth moves through space, how do the nulls move? It is worth noting that while Chris and I were thinking mostly of magnetic fields in 3 dimensions while doing this work, I will be sticking with 2 dimensions here in order to make it simpler to visualize. Everything we talk about can be extended to 3 dimensions in a straightforward fashion. So how do we go about looking for magnetic nulls? Space is a really big place, and we don't want to have to search everywhere. How do we even know if there are any in the area we are looking? One thing that often helps when trying to find a solution in a large space of possibilities is to reduce the number of degrees of freedom of the problem. For example, in our case, we might want to reduce our search area from 2 dimensions to 1 dimension. We can do that if we can come up with some constraint that would restrict our search to a 1-dimensional curve. And Chris and I started by finding a way to do exactly that. Our first thought was to consider conditions under which the external field and local field cancel. This occurs when the 2 fields have the same strength and are pointing in opposite directions. So, first we could pick out all the points where the local field's direction is opposite that of the external field. This is going to form a 1-dimensional curve. We can see why this is as follows. A direction in 2 dimensions is defined by an angle, and the space of all angles can be drawn as a circle. This space is 1-dimensional. The direction of a magnetic field at every point on the plane then gives a function from 2D space to this 1D space. At any point on the plane, there's at least one direction of movement that gives you rotation in one direction, and an opposite direction that gives you rotation in the opposite direction. Between these 2 directions of movement, there must be some direction that gives you no rotation at all. This is the direction in the plane along which the magnetic field points in a constant direction. Tracing out a path along this direction at successive points gives you the curve we are looking for. Working in 3 dimensions instead gives you a set of directions lying on the 2-dimensional surface of a sphere. This mapping from a 3-dimensional to a 2-dimensional space similarly forces you to have a direction of movement in which your place on the sphere is unchanged, giving you an analogous curve in 3D space. Once we have this curve on which the direction of the local field is opposite the direction of the external field, we just need to find the point on the curve where the local field and external field have the same magnitude. Since we said the local field decays to 0 as we move away from its source, there will always be such a point so long as the external field is not too strong. If we change just the magnitude of the external field without changing its direction, the null will shift to a different location on the same curve to the point where the local field's magnitude matches. It's interesting to note that the direction of the total field is also constant along this curve, although it switches direction on either side of the null. If we draw more of these curves, corresponding to different constant directions of the total field, we see that they converge on the null, where the concept of direction breaks down because the field is 0. The way these curves run into and out of nulls reminded us a bit of the electric field produced by positive and negative point charges. The suggestion that nulls carry something like charge was interesting, since we already knew that nulls carry a similar number attached to them called their topological index. Could these be related? So, what is a topological index? As we discussed earlier, the direction of a magnetic field gives a map from each point on the plane to a point on a circle. This can be written as some angle theta, which is a function of coordinates x and y. Now, let's draw some path that encloses a part of the plane. If we trace this path once around and watch how the angle changes, we see that no matter what the field or curve looks like, the angle always does an integer number of laps around the circle, since the magnetic field always has to come back to the same value when we get back to the start point. We call this number the degree of the function theta over the curve. If the direction the angle wraps around the circle is the same as the direction of the path around the curve, say counterclockwise, then the degree is said to be positive. If the directions of rotation are opposite, then the degree is said to be negative. Now we can define the topological index, or Poincare index, of a null. The topological index is just the degree of theta over any curve enclosing the null. As we saw a moment ago, circular nulls have index +1, and saddle-shaped nulls have index -1. Things work similarly in 3 dimensions. In order to calculate the index of a null, you wrap a surface around it and consider a map from this surface onto the sphere of field directions. Interestingly, the index does not change if we change the shape of the curve or perturb the field itself, so long as the null stays inside the curve. This is because the index has to be an integer, meaning that it can only jump discontinuously and ignores small changes. This robustness to small deformations is what we mean when we call the index topological. Let's draw a box around several nulls. What we find is that the degree over this path is equal to the sum of the indices of the nulls. We can understand how this works by dividing the path into smaller boxes that each contain one null. Going around each of these boxes in succession is equivalent to going around the whole original path once, since both of the internal lines are covered twice in opposite directions, canceling out. So, the degree of the function theta over any closed curve is the sum of the indices of the nulls inside that curve. This means that we can count nulls by drawing curves around them. This further drove our hunch of a connection to electric charges, since there's also a way of counting electric charges by drawing curves around them, which I will talk about next. The tool we will use to count electric charges is called Gauss's law. Gauss's law relates the flux of electric field through a boundary to the total electric charge within the boundary. Namely, it states that the flux, the total amount the field points outward through the boundary, is proportional to the enclosed charge. Double the charge gives double the flux. the 2D form of Gauss's law that we will use looks like this. It says that the total charge in some region is equal to the flux of the electric field through the boundary of that region. This integral here is a way of summing the component of the electric field pointing outward over the entire boundary. Now, let's go back to magnetic nulls. We have these objects that, much like electric charges, come in positive and negative varieties, can be counted by looking at curves surrounding them, and have streamlines that converge on them. It leads us to wonder if there's a vector field whose streamlines are these lines of constant magnetic field direction, and whether maybe there's some way of relating the index formula to Gauss's law. Maybe there is some vector field, similar to an electric field, that makes both of these things happen. So, what we would like to do is find some vector field whose streamlines are the lines of constant magnetic field direction we were looking at earlier, and that counts topological index the same way Gauss's law counts charge. We puzzled on this for some time. We felt there was definitely something here, but had not hit on the right language to tackle it. Then, during a Friday afternoon break for donuts and coffee, as we were talking over progress from the week, a caffeinated Chris suddenly said, "It's the pullback of the area form on the sphere." This was exciting because I immediately felt he had landed on the answer, even though Chris wasn't quite sure yet what he had meant. So, what did Chris mean? It's a succinct mathematical way of saying the following. We wanted to take this process of calculating the degree of the map and look at it as a continuous process. As we wrap around some part of the curve, theta covers some segment of the circle. We wanted to somehow encode this progress around the perimeter of the circle as the flux of some vector field through the curve, so that integrating this flux over the whole curve would yield the index. This meant pulling back the notion of arc length around the circle into something that could be summed over a segment of the curve. Thankfully, this process of pulling a measurement in one space into a measurement in a different space using some map between the spaces is a well-defined mathematical concept, one that can be calculated. So, armed with a more precise notion of what it is we were trying to do, I set to work late that evening, and without much trouble plugged through the three-dimensional version of a derivation I will now show for 2 dimensions. This calculation takes a few steps and involves a bit of vector calculus, so feel free to skip ahead if that isn't your thing. It's not critical to follow every step. What we want to find is some vector field v, such that the integral of its flux through some curve gives the sum of the indices of the nulls enclosed by the curve. We know that this sum is equal to the degree of theta over this curve. The degree is calculated from the total change in theta as you go around the curve, so it can be written as an integral summing infinitesimal changes d theta. We divide by 2 pi here, since we want the number of rotations, not the total change in angle. We want an integral over arc length ds, not over angle d theta, so let's fix that. Theta is a function of position, which is itself a function of arc length s along the curve. We apply the chain rule twice. And simplify. We see that this can be written with a dot product. This vector is the unit vector parallel to the curve. It is related to n hat, the unit vector normal to the curve, by a rotation matrix. If we plug this into the right-hand side of our original equation, we can match the integrands, obtaining an expression for v in terms of theta. We have solved for a vector field whose flux encodes topological index in a manner analogous to how Gauss's law keeps track of charge. So, does it have the other property we were hoping our vector field to have? Namely, is the magnetic field direction constant along its streamlines? This is easy to check. Such a vector field will be orthogonal to the gradient of theta, which we see to be the case. Because of this property, we call this vector field the isotrope field, from iso meaning same, and tropos meaning way or turn. The streamlines of the isotrope field, the curves along which the direction of the magnetic field is constant, we call simply isotropes. If we do the same calculation in 3 dimensions, using usual spherical coordinates, The formula for the isotrope field looks like this. This is the equation I drew a box around in my notebook that evening. It is possible to derive similar formulae for isotrope fields in 4 or more dimensions, although the expressions become more complicated. So let's look at the isotrope field of some nulls. We can see that it points out of positive nulls and into negative nulls, much as an electric field points out of positive charges and into negative ones. We can see that its streamlines, the isotropes, are in fact the paths of constant field direction we saw earlier. As an external field is varied, the nulls move along the isotrope corresponding to the opposite direction. Note that nulls of opposite sign seem to attract each other. The fact that the isotrope field points towards nulls makes it useful for locating them. If you can calculate the isotrope field, you can then just follow where it is pointing in order to search for nulls. The movement of nulls along isotropes means that they are also a useful means of predicting where nulls will move as their environment changes. In our paper, Chris and I use isotropes to constrain and understand how nulls move towards and collide with each other. Beyond this being a nice new tool for modeling magnetic fields, I think there is something more general being said here about vector fields. We considered only magnetic fields here, but you can derive the isotrope field for any other vector field in any number of dimensions. The isotrope field takes something topological, the indices of nulls, and singular points more generally, and turns it into a geometric object amenable to the tools of vector calculus. I expect this can find some utility elsewhere, perhaps for optimization algorithms or similar. I would love to hear your ideas in the comments or over email. A draft of our paper is available on arXiv, and we hope for it to be published in the near future. I would like to put together a more detailed written version of this video, as well as one for my previous video. The links will be in the video description. I would like to take a moment to thank the friends who helped make this video possible, in particular Chris, without whom none of this would have happened, and who provided some of the visuals and the title for this video, and Hardik, whose suggestions, including a few lines that appear in the script, helped keep this video on track. Until next time.